Hi, good day. My name is Davis Agwalam, and I'm here to do a presentation on the topic, a bidirectional LSTM approach to image captioning with scene features for my thesis. So basically, what are image captions? So if you look at the picture on the left, so that is a group of people beside a pool with fishes. So generating sentence descriptions for images. So moving on to some little introduction. Image captioning actually involves generating sentence descriptions, like I have already said. So it actually cuts across computer vision and natural language processing, as we have image inputs and we generate text descriptions as outputs. It also goes beyond just detecting objects in the image or simple classification, as the sentence descriptions generated should actually convey some level of semantic meaning. So to achieve this, previously, template and retrieval-based approaches have been used. So for template-based approaches, the generated sentences were not flexible, as they used already preset templates to fill in the detected objects in the image, and they actually conveyed very little semantic meaning. But retrieval-based methods were even worse, as they required large training data, and it could only retrieve captions for images which the model was trained with. So owing to the challenges of these two methods, deep neural networks have actually been adopted to improve this performance. So a CNN LSTM architecture has been commonly used, and this is known as the encoder-decoder approach, where a CNN is used to encode the image features and a decoder LSTM is used to translate these image features to output text sentences. So researchers have actually investigated different methods to improve the performance of this architecture, using embeddings such as POS tags or topic modeling or LDA to improve the performance of the architecture. So following this path of trying to improve the architecture using embeddings, this work, we adopt visual embeddings known as scene features and a bidirectional LSTM to improve the semantic meaning of the generated captions. So knowing that, that leads to the research question: to what extent can bidirectional LSTMs and scene exploratory features improve the semantic richness of automatically generated image descriptions? So moving further, before we go ahead, let us try to define some key terms. So basically, what are scene features? Scene features are the features extracted with the convolutional neural network that are able to identify background scenery in the image. So let's say you have dogs running in a park or people eating in a restaurant. So we extract features from the image that are able to tell the scenery or the location where the activities in the image are happening. So this actually helps improve the semantic meaning by bringing out the context between the images, between the objects in the image. So another thing is, why bidirectional LSTMs over unidirectional LSTMs? So bidirectional LSTMs have the ability to take into consideration both past and future context information during the word translation sequence, but unidirectional LSTMs are only limited to retaining information from past time steps during training. This limitation of unidirectional LSTMs and performance of an ability of bidirectional LSTMs make bidirectional LSTMs better for longer sequences. So moving on, having known all that, we try to define the aims and objectives of this research. So first of all, we try to investigate the state-of-the-art research for image captioning, and we adopt best practices in this domain to guide the major decisions. After that, we actually design a framework encompassing each section of the research implementation and proposed novelty. After the framework is set, then we implement this proposed CNN by LSTM approach while conducting different experiments in stages for effective comparative analysis. So we conduct experiments without each of the features we are proposing to actually measure the impact of these features when we introduce them. So after that, we evaluate the performance of the approach using standard evaluation metrics such as the bilingual evaluation understudy or the recall-oriented understudy for distinct evaluation, which are popular metrics for image captioning evaluation. So the methodology, this is actually the methodology followed to carry out this research. The process is shown in this flow chart. So first of all, we collect the data from the public repository and we separate the data into images and the captions. Then we process the image and text before we extract features from them. So if you see for the image, we extract both global image features and the deep scene image features. So after feature extraction, we use those extracted features to model, and after modeling, then we conduct inference and evaluate our results. So, so the steps are the data collection, the data processing, the feature extraction, modeling, inference, and evaluation. So to discuss these in detail, we'll collect the data from Kaggle. So the Flickr 8K benchmark dataset. The Flickr 8K dataset is a benchmark dataset for image captioning research, and we chose to use it in this research because of its fairly small size and the limited computing resources. So it is quick for prototyping and will be good to conduct the experiments we are trying to conduct. So for data processing, we compress the images to the input shapes of the pre-trained CNNs that will be used to extract the features, and we scale the pixels within 0 to 255. So that is the processing for the images. For the text, first of all, we convert the text to lowercase, we remove punctuations, we remove numbers, we indicate start and end tokens to identify the beginning and the end of the sentence to the model. And then we tokenize, we break this model into, we break the sentence into subsequent words. Then we vectorize these words as numbers using word to ID and ID to word dictionaries. So for feature extraction, we extract the global image features with the inception v3. So this model is focused on extracting the objects in the image of extracting the items or the objects in the image, like I said, and the deep scene image features are extracted with a VGG16 places 365 pre-trained CNN. So this is the CNN that is tasked with extracting the scene features from the image. And these are the features we're going to use as visual embeddings to try to improve the performance of the model. So looking at the modeling approach, the diagram is shown on this slide. So first of all, we have the encoder and the decoder side of the model. So you can see that this is an image of dogs swimming in water. So we use the inception v3 model to extract the global image features, which results in a feature vector of 1 by 2048. Then we use the VGG16 places 365 CNN to extract the deep scene image features, which gives a feature vector of 1 by 4096. Then we pass that to model. So the global image feature input model contains an input layer and a dense layer, and finally a repeat vector layer. We do the same thing for the deep scene image features. Then we concatenate their outputs into one feature vector. So for the partial text inputs, we vectorize them. That's converting them to numerical. Then we put them into a text input model, and the length is 1 by the max length. And for this research, the max length was found to be 37. So for sentences that were not up to 37 in length, they were padded with zeros to get to this max length. Then inside the text input model, we have the input layer and an embedding layer. So we use the embedding layer to learn the vector representations of each of these words. So this is a better approach compared to other methods like one-hot encoding, as it does not generate very sparse matrices, which is usually the case with one-hot encoding. So after we have the output from the embedding model, we concatenate the output with the concatenated image feature output already and pass it to an LSTM, a by LSTM network, using a softmax activation function to actually generate the descriptions. So we have dogs swimming in water, and the model will finally generate dogs swimming in water. So that is the modeling approach. So for inference and evaluation, after going through literature review, we found out that there are actually two methods to perform inference for image captioning tasks. So we have the greedy approach and we have the beam search approach. But from literature review, the greedy approach always gives better descriptions than the beam search approach. So we adopted the greedy approach to perform inference in this research. So for the evaluation metrics, I stated earlier, we use the bilingual evaluation understudy, which is the blue, and we use the recall-oriented understudy for distinct evaluation, which is the rouge, to evaluate this research. So the implementation, now we have the setup. So this is the hardware setup that we use to implement this research. So we have the machine was actually a MacBook Pro and with the Catalina operating system. So the RAM was 16 gig and we had the Core i7 processor and a 256 GB hard disk. So we actually used some cloud compute to implement this research, especially for the modeling, as we could not run models on the local machine, even though we process the data on the local machine. So Google Colab offers a free Tesla K80 GPU with 242 496 CUDA cores and 12 gigabyte RAM. So for the software, we used Python 3.7.4 as part of the Anaconda distribution to implement this. The IDE we used was the Jupyter Notebook, which is also part of the Anaconda distribution, and the cloud environment was the Google Colab. We implemented all this in a Google Chrome browser. So after discussing the hardware and the software setup, then we moved into handling the data. And after doing all the data processes that we defined earlier in the methodology, this was the result. So this is an example of a scaled image, the scaled image within 0 to 255 and cleaned text captions. You see that the beginning and the end tokens are inserted into the text to be able to identify to the model the beginning and the end of the sentences. So the model architecture defined are shown in details here. So this CNN LSTM model architecture is the first one. You can see that the input is the global image feature vector. The global image feature vector that was talked about earlier. You can see that the input shape is 2048. So we pass that to a dense layer to further compress it from 2048 to 300. Then we pass that to a repeat vector layer to repeat this vector across the entire length of the training sequence. So this is the text input. You see that the max length is 37. So we input the text sequences, we pass them to an embedding layer which maps the words to a 300-dimensional vector. Then we concatenate the outputs from the global image features and the text image features in this layer before passing it to an LSTM layer, and finally a dense layer to predict the probability of a word being the next in the prediction sequence. So for the second architecture, for the second model, we extend this architecture by adding one more input. You see, this is the same features now that we have introduced into the model. So the global image features were 2048 dimension and the same features were 4096. So we introduced them, as said earlier, a dense layer and a repeat vector layer to repeat it across the entire text sequence. We concatenate them, then we bring in the text, we concatenate them here before passing into an LSTM and a dense layer to predict the probability of a word being the next in the prediction sequence. So for the third model architecture, it's the same inputs, but now we bring in the bidirectional LSTM to check if performance will improve. So like I said earlier, these experiments are conducted in stages. First of all, we start with the normal architecture without the same features or the bidirectional LSTMs. Then we introduce the same features. And finally, we introduce the bidirectional LSTMs to be able to, measure the impact of each of these proposed items on the model. So I would like to conduct a small demo here before discussing the results. So let me share a new screen. So this is the code for the research. So we imported the libraries. You can see the libraries for the modeling, libraries for visualizations, and libraries for data handling, the other dictionaries and the default dictionaries. So we loaded the data from file. This is the file path that we generated, that we downloaded the data and kept. So we use this function to load the train, the development, and the test sets from the file paths. So if you look at the train, it contains image names. So we actually dump this to pickle file so that we can always have access to it at a later time. So this is a sample image in the training set. So if we change this to 27, you see this is an image in the training set. We change this to 28. This is another image in the training set which we want to generate captions for. So moving on, we use the Inception v3 model to extract features from the images. So you can see that this get image function, we resized the images to inputs of 299 by 299 so that they would fit this Inception v3 input, and we scaled them to 255. So we already downloaded this Inception v3 from Keras applications. So we just load ImageNet weights. Then this is a summary of the ImageNet model of the Inception v3 model. You can see it's a very deep convolutional neural network. So we set up the model to use the second to last layer of the model to extract image features. And we define a generator to progressively load and extract these image features because we didn't want to load all the images into RAM at the same time due to computational limitations. So we did that for the train and the other sets. So we save the files for future access. So to properly save the files, we convert them to an ordered dictionary so that we can have the image name and the values for that particular image. So we do that and we save it to pickle files so that we can have access to it later. We do the same for the training set. So after extracting the global image features from the images, it is time to process the captions. So we read in the captions while adding start and end tokens like was discussed earlier. So we call this function to read in the captions. And after reading in the captions, we clean the captions. We remove punctuation, we remove numbers. So we dump the clean text we dump it to Pico so we can have access to it later. And if you look through these results, you can see that the text is clean. We have a black dog, no punctuation. You have start and end tokens. So we can see that the text is actually clean. Yeah, and this is the other dictionary that we created. So we have the image name, and then we have the accompanying caption. So each image has 5 ground truth captions. So after that, we convert, we create word to ID and ID to word dictionaries that we would use to vectorize these words in the captions. So we find out the max length for our training set, which is 37. So like I said earlier, due to computational resources, we are using a training generator to progressively load the images into the model progressively load the data into the model during training. So we are loading it in batches of 128. So this is the code to create the first model. And if we do that, this is the output that we have for the first model. We have a total of 6,428,000 parameters thereabout. So we define a checkpoint and we use early stopping to try to overcome overfitting. So this code is to load the model weights if you already have them trained. So this is where we fit the models, but we do not fit the models here. We fit them on Google Colab as there is a GPU there and there's no GPU on this host machine. So after we fit that, we save the model weights at 5, 10, and 15 epochs. So for the experiment 2, extracting the scene features, we use and external implementation of the VGG 16+6365. Again, we compress the image to 224 by 224 input for the VGG 16 model, and We scale it to 255. Then we instantiate the model, you can see this is another deep architecture, though not as deep as Inception v3. We do the same thing, setting up the model to use the penultimate layer to extract the features. Then we load, we progressively load the image for extraction using a generator like was done earlier. So we do that for the training and the test sets. And like was done earlier, we converted them to other dictionaries so that we can have the images, the image name to be the key and the value to be, and the feature array to be the value. So we dump that to Pico so that we can have access to it when we are modeling in Google Colab. So like was done earlier, we also use a generator to progressively load the images during the data during training, I mean. So we define the model for experiment 2. So this is the model architecture. We see now that we have 7,964,000 parameters to train. That's going up from the first model. So we load weights. If this file already exists, then we create a checkpoint part, then we checkpoint the model, and we use early stopping to monitor overfitting. So again, we feed the model. This is done on Google Colaboratory as there's a GPU there to properly feed the model. So fitting the model takes about 12 to 13, or maybe, yeah, around 11 minutes for each epoch. So moving on to experiment 3, now we improve the capacity of the model using bidirectional LSTMs here. So this is the architecture of the model. You can see that the parameter size has increased, therefore the capacity of the model to learn has increased. So we do the same thing that we have been doing before. Define the checkpoint part, checkpoint the model, and use early stopping to monitor overfitting. Again, we do not feed the model here, we feed the model on Google Colaboratory. So moving to inference, now we have, like was discussed earlier, we're using the greedy approach. So this is the code for using the greedy approach to generate sentence descriptions. So here we use the defined models to make predictions, and here we are using the model 3 for the third experiment to make predictions. So this code is to evaluate to make predictions across the entire test set and return the actual and the predicted captions. So this is the code used to calculate the root score. Then this is the code used to remove the beginning, the start and the end tokens before evaluation. So we load the model weights here, evaluate the model. This takes quite a few minutes to run. It takes about 5 minutes to run. Then we strip the tokens from the output, and then we run the evaluation. So there we see that we have the blue scores of this 46.7. If we do the road score, it takes quite a few minutes to run. We have 25.7 for the road score. So this is at 5 epochs for experiment 1. So for experiment 2, we load the experiment at 10 epochs, run the evaluation again, remove tokens. And if we run the blue scores, we get 53.122, 32.8 and all that. So we can see that the performance improves at 10 epochs. So we run the ROGE. So we see that the performance actually improved from 10 epochs. For 15 epochs, we've already run this. You see that the performance actually dropped. So now checking some predictions. So we have this here. It says a man in a red shirt is climbing a rock. So this is for experiment 1. So yeah, from the image, we can see that there are rocks in the image, and there's a boy, though he's wearing a white shirt, he has a red stripe on his shirt. So if we try another prediction, let's say we predict for image 5, we have, so we have a brown dog is running through the grass. So this is the predicted caption, and these are the ground truth captions. So moving on to experiment 2, we load the weights, do the same evaluation across the entire test set and strip the tokens. Then we evaluate based on blue scores. And this is what we get at 5 epochs. And the Rouge score is this. So we can see that at 5 epochs, we have blue 1 of 49. So moving on to 10 epochs, we load the experiment at 10 epochs, evaluate the model. Then we have the actual predicted and the actual and the predicted sets. So we run the blue again. I already have some of these pre-run because they actually take time to run. So I just have some of them pre-run, so we can only run the parts we need. Then we do the Rouge score. We can see that the performance improved at 10 epochs. So it dropped again at 15 epochs. Let's just move straight to the predictions. So if we try to predict, let's say image number 18. So we have a dog runs through the grass, and this is the predicted caption, and these are the ground truth captions. So we can see that we are close. Then we run, moving on to experiment 3, we load the experiment 3 weights at 5 epochs, run the evaluation, strip the token, and run the same blue score. We see these are the blue scores. We run the same for the Rouge. They take quite a bit of time to run. So like I said, I have them already. I have some parts of them already pre-run. And I will be submitting this entire code sequence. So you can actually run this from the very top. And yeah, so we do that for 10 epochs, same thing. Then what we can see that at 15 epochs, again, the model performance drops. So if we check predictions, let's run this number 5. So we can see that this one generates a brown dog is running through the grass, while these are the other captions. We can also see that these models are able to actually generate words that are not in the reference text, so there is no true here, but the model is able to generate the word true. So if we do this for 18, yes, okay, says a brown dog is running through a grassy field. Now we can see the scenery being brought into the caption. So again, the word field does not exist in the references, but the model is able to bring in this word field, thereby making the captions more semantically correct. So this is just a presentation of the results. We just put the values and plot them. So moving back to the presentation, now we are done with the demo. So moving back to the presentation, we discuss the results and the evaluation. So for the experiment 1 model now, we see that the model peaks at 10 epochs. We see that the model peaks at 10 epochs with the highest blue score of 53.1, 32.9 for blue 2, 22.6 for blue 3, and the highest Rouge score. Though at 15 epochs, the blue 4 score was actually higher. So for the second experiment, we see that though the model peaks at 10 epochs, the performance doesn't perform as well as the model from the first experiment, as you can see. As the model result was 51.8 here, and the blue 1 score here was 53.1. This actually indicates that introducing the same features reduces the performance of the model. So to solve that, we actually investigated that by introducing the bidirectional LSTM to improve the capacity of the model to learn, and we can see that that made a positive impact. As we can see that we have a very high blue 1 score of 55, which is the highest we have gotten so far. And we can see that this is at 5 epochs, showing that the model trains and converges faster. We can also see that even at 10 epochs, when the model has started to decline, it performs better than the maximum one for the same features. This actually further buttresses the point that bidirectional LSTMs improve the performance over unidirectional LSTMs. So this is the plot that was discussed earlier in the code. So basically, we can see here that the CNN by LSTM with same features actually outperformed these other models. So we did some qualitative evaluation. So for this first image, you will see a group of people are standing in front of a crowd. That is the CNN by LSTM with scene features. We can see that the model with just scene features and a unidirectional LSTM actually did not give a very good prediction. It actually gave a worse prediction compared to the first one, which confirms what we said earlier. But we can also see that the introduction of the scene features brought this a group of people, as you could see from the background, that there are a lot of people in the image and in front of a crowd. So that is it for the first image. For the second image, you look at the reference text, two brown dogs run through a grass together. So again, our CNN by LSTM method is able to introduce scenery. So you see the words grassy field. So if you look at this image, you see a grassy field. So it is able to introduce what is going on in the scene into the image, into the sentence description, thereby generating more semantically correct sentence descriptions. And for the final one, we see that the CNN by LSTM method also brings in that scenery when it says a man in a red shirt is climbing a rocky wall. So if you look at the image, it looks like this boy is climbing up a wall. So, but if you look at the other captions, the word wall is not there. So this CNN by LSTM combination is able to bring in correct scenery to be able to improve the semantic quality of the generated captions. So finally, for the conclusion, the limitations, and the future work. So restating the research question, this research actually investigated to what extent features and to what extent scene features and bidirectional LSTMs can improve the semantic richness of automatically generated image captions. Yeah, so as one of the major findings of the research, we actually saw that this combination of scene features and bidirectional LSTMs can improve the semantic richness of the generated captions, and especially for longer sequences, thereby, backing up the thesis that bidirectional LSTMs perform well for long captions. So we actually also found out that introducing scene features with unidirectional LSTMs inhibits the performance of the model, as was seen from the results. When we brought in the scene features, the performance actually dropped from the ordinary CNN LSTM model. When we introduced the scene features, the performance dropped. So we also found out that bidirectional LSTMs improve the model capacity and subsequently improve the performance of the model. While there is this improvement, one should also be very careful, as it makes the model train and converge faster, thereby making it more prone to overfitting. So to discuss some of the limitations of the work, we used the Flickr 8K dataset. This dataset is fairly small, as it contains only 8,000 images. There are larger datasets like the MS Coco and the Flickr 30K, but due to computational limitations, we used the Flickr 8K dataset to be able to conduct a proper experiment. So we, as also part of the limitations, we did not pursue hyperparameter optimization to further refine the model architectures. This could potentially have improved performance, but it was not pursued, once again, due to computing resources. So for future work, one can bring in the attention mechanism to map the word vectors to the actual image regions during word prediction. And this would also help in bridging the gap in modality between the image and the text data modes, and maybe subsequently improve the results. Thank you very much for listening.